everyone. I wanted to show you how to use SALT for computing probabilities from a normal distribution. You may have come across some homework questions that start with this. You may need to use a table or technology to answer this question. Well, the link to the table does go to a table. You would end up using not a t-curve, but a standard normal curve. And you could find your z-score and find a second decimal place and find a number that is the area to the left of that z value on the curve. So 0.0735 area is to the left of a z value, negative 1.45, which is kind of clunky, and that's the way you would do this if you didn't have a calculator around. You can use technology to answer these questions, but I find that this technology here is very clunky and you have to use z-scores and it's just not very friendly. But we have another option, and that is to use SALT. So if you go to SALT and then choose distribution calculator, you can choose a normal distribution. That's what we're working with. And you can set the mean and the standard deviation to be whatever you need it to be. So for example, here's a pretty typical question from chapter 6. Now what's typical about this is it starts off by saying, oh hey, we have some data that has a normal distribution. Here's the mean, here's the standard deviation. Now let's ask some questions. Find the probability that a baby weighs more than 4,000 grams. Another question, weighs less than 2,000, more than 4,000. And then here's another question, it's kind of backwards. What birth weight describes the 25% of weights that are the greatest? So what's typical about these questions is that we're asking probabilities in different parts of the normal curve. If we go back to the normal curve here, which is a little bit bigger than my screen, you'll see that here's this bell-shaped curve, the normal curve. Here's an area that's shaded to the left, but if we choose a different button, we can find an area that's shaded to the right, or we can choose two shaded areas, and these areas can be the same size or they can be different. You can change the z-scores there, or we can find an area between two values. Again, we can edit these numbers here to be as big or small as we need them to be. You can also change the x values, not just the z values. So what we have on this graph here is we're graphing something, so there's an x and y axis. On the y-axis, this is our function f of x, and this axis is really just telling us height. We don't use it ever. So you can kind of forget that it exists. But down here on the x-axis, it's actually labeled twice, once with x and once with z. So if we end up changing the scale of our data, like right here, mean distribution weight 3,500 grams. So if I go to this mean and change it to 3,500, and then change the standard deviation to be 540, now we have this same bell-shaped curve, but we get two labels. We get an x label and a z label. The x label is the values of our data. So the mean is 3,500, the standard deviation is 540. So you can kind of see how the tick marks go out to about 3 standard deviations from the mean, either way. And then in z values, we have a mean of 0, the standard deviation is 1. So here we got 1, 2, 3, 4 standard deviations from the mean. And the negative z values mean below the mean. We don't have negative weights because, well, that doesn't make sense. But also, these numbers are still positive. They're just below the mean. So they still correlate to one another. So it's kind of nice to see these two scales and say, oh, well, what's 1 standard deviation below the mean? 0 minus 1. Oh, well, that is 3,500 minus 540. So what can we do with this distribution? we can change these probabilities. We can change these cut points that are listed here in these boxes, and then we will get a probability in the answer. Same thing over here. If we want to use z-scores instead of these x values, we can change those. We can also move along here. We can change left, right, both tails. Again, they don't have to move in tandem. You can change one or the other. And then we can compute probabilities or proportions of the graph that are shaded. So let's go to a question. Part A here, one common medical definition of a large baby is any baby that weighs more than 4,000 grams at birth. What's the probability that a randomly selected Canadian baby is a large baby? So this is the real question. What's the probability of randomly selecting a baby and it's large? And then we have a definition. Weighs more than 4,000 grams. So we want to look for words like more, less, between, outside, extreme, within. Those are all words that tell us where in the graph we're going to be putting the yellow. So in this question, it said more than 4,000 grams. So more than means bigger numbers, so that means right numbers on the axis. So I need a right tail graph, and I need the cutoff to be 4,000 because that's considered large according to that definition. Now, we're not going to quibble about the definition of large. We're just going to go with what they say. So the probability, so P parenthesis, probability of X, and this is a greater than sign, and we need to change this number to 4,000. You can use the little up arrows, or you can just change that number to be 4,000. Type in, push enter. And what happens is the graph shaded area changes, the cutoff changes, and then the probability down over here in this bottom box also changes. So this yellow shaded region is the area 0.17724, so about 18%. So if we go back to the question, we would say, what is the probability that the randomly selected Canadian baby is a large baby? Round out to 4 decimal places. Okay, so we have 0.1772. Check our answer. Great. Okay, second question. This one's a little different, but it kind of has the same idea. What's the probability that the randomly selected Canadian baby weighs either, so that's a keyword, less than 2,000 grams, or, another keyword, more than 4,000 grams? So 2,000 and 4,000 are our cutoffs, but we're not looking between 2 to 4,000. We want less than 2,000, more than 4,000. So we're talking about the extreme ends of the distribution. So if I typed in, once I get my correct choice, I need both tails. 2,000 is my lower cutoff, so always put the smaller number first, and then the bigger number, 4,000. Here we go. Notice how it went red there? It's because it thought I was going to put an answer of 400, and it was warning me because 400 is smaller than 2,000. That's not right. But as soon as I got that third zero in there, it went correct. So here we go. X less than 2,000 or X greater than or equal to 4,000. Oops, maybe I should have said less than or equal to. So notice that word or. That's because you can't be in this yellow region and that yellow region at the same time. You can be in one or the other. So this is the math or that is about discrete or not discrete, but disjoint sections. You can only be one or the other. But since we want to know the chances of being in one or the other with these disjoint sections, we can just add up the probabilities to get our answer. And that's what it has already done for us. It added up this tiny little area and then the bigger area to get a total of 0.17998. So about an 18% chance of being extremely low birth weight or a large baby. So it's kind of looking at extreme weights. That's what this question's asking about. So what was my answer? 0.17. If I do some rounding, looks like 99. 0.1799. Okay, that's looking good. And then the third question is a backwards type of question. It's saying, what birth weights describe the 25% of Canadian babies with the greatest birth weights? So if we're looking at our distribution, so far we have put in values of X and then we get out a probability. Well, this time we're going to put in a probability, 25%, and then we're going to get out an X value or a weight. But we need to choose the right type of graph. We want 25% of Canadian babies with the greatest birth weights. So we have to be smart and realize that great weights are over here on the right side, so we need to pick our right tail. And then we can put in our probability, our shaded area. For fun, you could drag this shaded area and see what happens. Get kind of close to 25%. You could even probably, with enough precision, get the answer just by yourself. But I'm going to go ahead and edit this a little bit, push enter. So here's my 25%. And then this is the weight that is the cutoff for that upper 25%. You could even say that this is the third quartile because the lower 75% is separated from the upper 25%. So how do we type in our answer? It says round to 4 decimal places. So let's get 4 decimal places. 3864.2245. It looks like I could just copy that, paste that, check score. Super. There we go. So what I've shown you using SALT are 3 different typical questions that we use with a normal distribution. Some other questions that we didn't see that you might use are, what's the probability that a baby's weight is less than 2,900 grams? Or what's the probability that a baby's weight is between 3,300 and 3,600 grams? Yeah, I think that kind of covers it. So left tail questions, right tail questions, both tail questions, which you can adjust. They don't have to be symmetric. And then between questions. And again, these don't have to be symmetric. They can be, very much above. Let's adjust that. There we go. So there's kind of a chunk on the right tail. You could even put in a z-score of 10 if you wanted, which is then the same as a right tail probability, because 10 is pretty far off to the side. It's, getting close to infinity, if you will. This is just one type of calculator to compute probabilities. There's other ones out there, but it's pretty nice to use.